Here's something that should not be true. Add 0.1 to itself 10 times in Python, and the answer is not 1. This is floating point error, and to understand why it happens, we need to see how computers store numbers in binary. That intuition is also the precursor to the approximation algorithm coming next. So far, we've seen two numeric types in Python. Integers are whole numbers. Floats are real numbers, the ones with a decimal point. Most of the time, floats behave the way you expect, but some surprising things happen when you compute with them. Those surprises are the motivation for talking about binary numbers, then fractions, and then floats across this lecture and the next. We start with a concrete example. Here is the example. We start with an integer variable set to 0, then loops through range of 10, which runs the body 10 times. Each pass adds 0.1 to the running total. So we are adding 0.1 to itself 10 times. Then we print whether that sum is equal to 1. When we run it, Python prints false. That is not intuitive. Add 0.1 10 times and you expect 1, but the program disagrees. To see what is really going on, we print the sum itself, and we also test whether it equals 0.1 multiplied by 10. The loop sum comes out as 0.999 and a long trail of 9s, while 0.1 times 10 gives exactly 1, as expected. What we just saw is called floating point error. Because it happens, you cannot test floats for exact equality. You cannot use the double equals operator between two floats because results like this will quietly break a program. Imagine something as simple as adding 0.1 to itself 10 times, failing to equal 1, deep inside a calculation. The big idea is that every operation on a float introduces a tiny error because of the way floats are stored in memory. Each error is minuscule, but the more operations you perform, the more it accumulates, leading to surprising results. To understand why, recall how the computer represents numbers. The computer works in binary, only zeros and ones, while humans work in base 10, thinking in digits from 0 through 9. The computer uses base 2 because of how its hardware is built. It is easy for hardware to represent a magnetic spin as up or down, or a voltage as low or high, that is 0 or 1. It would be much harder and would introduce too many errors for the hardware to reliably distinguish many levels, like 0, 1/10 of high, 2/10 of high, and so on. So it is far simpler and more reliable for the hardware to sit in just one of two states. That is where binary comes from. When we deal with integers, this base 2 storage is not a problem because we can convert any whole number from base 10 to base 2 exactly. The trouble is with floats, where some fractions have no exact binary form. You don't need to know how to do the conversion yourself, but seeing how whole numbers convert gives the intuition for what goes wrong with floats. So let's convert a whole number to binary. Consider the number 1507 in base 10. We can decompose it as 1 times 1000 plus 5 times 100 plus 0 times 10 plus 7 times 1. Each digit, a value from 0 through 9, multiplies a power of 10. The rightmost digit multiplies 1, the next multiplies 10, the next 100, and so on. Each place worth 10 times the one before it. Base 2 follows the exact same pattern with two differences. Each digit is only 0 or 1, and each place is a power of 2 instead of a power of 10. So the places are 1, 2, 4, 8, 16, and onward, doubling each step. To convert 1507 to binary the human way, we ask, what is the largest power of 2 that fits without going over? 2 to the 11th power is 2048, already too big. 2 to the 10th power is 1024, which fits. Subtract it, and 1507 minus 1024 leaves 483 remaining. Next, the largest power of 2 that fits in 483. We skip 2 to the 9th, which is 512. Too big? 2 to the 8th power is 256, which fits. leaving 227. Then 2 to the 7th, 128, leaves 99. 2 to the 6th, 64, leaves 35. 2 to the 5th, 32, leaves 3. Now the small powers, 2 to the 4th is 16, 2 to the 3rd is 8, and the 2 to the 2nd is 4. All bigger than the remaining 3, so they contribute zeros. 2 to the 1st power, 2 fits, leaving 1. And 2 to the 0 power, 1 fits, leaving 0. So 1507 equals 2 to the 10th, plus 2 to the 8th, plus 2 to the 7th, plus 2 to the 6th, plus 2 to the 5th, plus 2 to the 1st, plus 2 to the 0. Now read off the bits. Line up every power of 2 from the 10th down to the 0th. A power we use contributes the bit 1. A power we skipped contributes the bit 0. 2 to the 10th is 1. 2 to the 9th skipped is 0. 2 to the 8th, 7th, 6th, and 5th are all 1s. 2 to the 4th, 3rd, and 2nd are 0s. 2 to the 1st is 1, and the 2 to the 0 is 1. Reading top to bottom gives the binary number 101111000011. The human method works, but there is a more systematic recipe that a computer can run, an algorithm you will never have to invent, but should be able to code once it's given. Look at the remainder when you divide the number by 2. If the number is odd, the remainder is 1. If it's even, the remainder is 0. That remainder is the last bit, the farthest right bit. Then integer divide the number by 2 and repeat, prepending each remainder to the front. Let's trace 1507 through this recipe. 1507 is odd, so prepend the bit 1. Dividing by 2 gives 753. 753 is odd, prepend the bit 1. Halving gives 376. 376 is even, prepend the bit 0. Halving gives 188. 188 is even, prepend the bit 0. Halving gives 94. 94 is even, prepend the bit 0. Halving gives 47. 47 is odd, prepend the bit 1. Halving gives 23. 23 is odd, prepend the bit 1. Halving gives 11. 11 is odd, prepend the bit 1. Halving gives 5. 5 is odd, prepend the bit 1. Halving gives 2. 2 is even, prepend the bit 0. Halving gives 1. And 1 is the last number, so prepend the bit 1. Reading the prepended bits, we get 10111100011, exactly the same binary number as before, but obtained by simple, iterative, loop-based code. Both methods give the same bits. The human method reasons about the largest powers of 2. The algorithm just records remainders in a loop. For a negative number, we simply put a minus sign in front of the result. So binary is why floating point error exists. Some fractions can't be stored exactly in base 2, so floats carry tiny errors that accumulate. That's why we never compare floats with double equals. Next, we'll use this to build an approximation algorithm. To practice what you just learned, this course has free exercises and AI-graded feedback on ludium.ai. The link is in the description.